All right, so I always thought this was really funny that in this course we get into the definite integral, which is the fundamental, it involves the fundamental theorem of calculus, and we're literally like near the very end of the entire course is when we're actually talking about, hey, this is the most important thing in calculus. But in any case, let's go through these notes here because I think this is really like a good representation of what this course is all about. It's really about the definite integral, okay? So the definite integral, last time we talked about finding Riemann sums, if you do a left-hand Riemann sum or right-hand Riemann sum, what specifically happens when you increase the amount of rectangles used to approximate the area under the curve. And that, sure enough, you get closer and closer and closer to the true value. So that's pretty much what the definite integral is. I assumed you probably were recognizing, hey, like there's probably going to be something to do with integration that we have been talking about for the last entire chapter. But in any case, the definite integral of a positive function over an interval from a to b is the area between f, the x-axis, x equals a, and x equals b. So another definition is the area under the curve between a and b. Or another way, if you have a positive rate of change, then the definite integral is the total y units that accumulate between a and b. So in other words, the way that we write it is just like we do previously with the long extended s. There's the integral sign. And we indicate the lower and upper bound literally just on the bottom and the top of that integral, okay? So I want to point something out. I literally didn't even realize this until I put this content together, but I'm just like, wait a minute, that makes sense. The integral sign is a giant extended S, and the Greek letter sigma both start with the letter S. So it's essentially like a summation. There's a summation that's tied in there. And here is quite literally what the definition of that integral is, okay? The integral from a to b of f of x. So I want to point something out. This sum with all this stuff at the very tail end, that's basically just a Riemann sum, okay? So you have your n value. You can segment it into, 4, 5, 6, 7, however many rectangles you want. But let's just say that that's an n value. If you take that value and you send it all the way to infinity, what this is saying is you're segmenting it into an infinite number of rectangles, which is just the area under the curve. So that's kind of how we get closer and closer by adding more and more subintervals, okay? So that's effectively what the fundamental theorem of calculus it is. It leads into that. So if you have a continuous function on a closed interval from a to b, the definite integral of f exists on this interval, and the integral from a to b of that function is the integral evaluated at b minus the integral evaluated at a. So we'll go through some examples here, but I do want to show you kind of what this looks like. So first and foremost, we want to find the integral from 2 to 4 of 3 square root of x dx, okay? So let's first change this x into something with a positive exponent. So it's not like a square root that we have to worry about. So here we've got 3x to the 1/2 dx between 4 and 2. We're kind of going to ignore the bounds here really quick. Okay. First, we have to find what the integral is. So we can pull the 3 out. We do the integral of x to the 1/2, and you're going to notice that it's 1 over 3/2, which is 2/3. 2/3 times 3 is just 2. And then we're increasing the exponent by 1. So 1/2 plus 1 is going to be 3/2. And then what we do at the very tail end, after we do the integration of the stuff on the inside, we're going to draw a really long line and include our bounds. So we've got the 4 and the 2 right there. Simplify some stuff. This is the same thing as above. It's just, simplified. And then what we do, once we get to the point where we're going to evaluate, we take the upper bound and we sub it in for 4, and then we take the lower bound and we sub it in down below as well. So we take the upper bound and then we subtract the function with the lower bound. So you can see pretty much kind of duplication here, except we're subtracting one from the other. But I want to point something out really quick. In this example with the definite integral, I included the plus c, but in practice, when you're using a definite integral, the constant terms are always going to cancel out. No matter what, 100% of the time they will cancel, okay? So you have a constant here, and then you subtract off that constant there, they're always going to go to 0. So in general, when you work on definite integration or definite integrals, we're going to just ignore that plus c. So this is kind of what it works out to being, which is approximately 10.343. Okay. All right, let's go ahead and bounce through some examples here. Let me go to my whiteboard really quick. And let me close this. Okay, so let's go ahead and do some problems. Again, a lot of this stuff is going to be very similar to stuff that we've done. There's a few added steps. So we're going to use some U substitution. We're going to do some other things, but I want to point a couple of things out as we do this. So number one, let's just do the integral from 0 to 3, 4x dx, okay? So I'm going to do the integral first, okay? So I'm going to raise the x to the second power, and then I'm going to divide by 2. So 4 over 2 is actually going to be 2x squared. And again, remember, because I'm doing a definite integral with bounds, I don't have to worry about the c. So I'm just going to do this between 0 and 3. All right, so this right here is the same thing as 2 times 3 squared minus 2 times 0 squared. So we do our upper bound of the function minus the lower bound of the function. So this right here is the same thing as 3 squared times 2, which is 18, minus 0, which in this case is just 18. Okay? So that's our solution. All right, let's do another one. So suppose I have the integral from 1 to 8 of 2 dy. 1 to 8 of 2 dy. So 2 dy is the same thing as 2y, right? When I take the integral, it's just going to, the differential is just going to transform into that y, and then I'm left with a 1 to 8. And now I just do the 2 times 8 minus 2 times 1, which in this case is going to be 16 minus 2, which is equal to 14. Okay. This one actually kind of makes sense because if you think about 2 as being like a constant term, from 1 to 8, it's a gap of 7. So 7 times 2 should be 14, which is exactly what our solution is. So that's, in this instance, it kind of is an easier one to work out. If you look back on the previous notes from section 13.1, that very top section of the notes where we talk about like the rate and it's a constant rate, that basically is what this is right here. It's just a constant, it's a constant rate. And so the interval is just 7 units long, and so we just do 7 times 2 and we get 14. So again, it only works kind of like that in this instance, but let's go ahead and do another one. So suppose I go from 0 to 2 of x to the 4th minus 5x cubed plus 2x dx, okay? So first off, let's do the integral. So this is going to turn into 1/5 x to the 5th. This is going to increase to the 4th power, and I'm going to be dividing by a 4 then, x to the 4th. 2x. I increase it by 1 to the second power, then divide by 2. So this is just going to turn into an x squared. And then I'm evaluating this between 0 and 2. Again, you can ignore the c's when you do definite integration. The indefinite integrals, you have to include the c. For these ones, you do not need to include it. So 1/5. Now let's evaluate. 2 to the 5th power minus 5/4. 2 to the 4th power plus 2 squared. And now listen, this is the important thing. We need to make sure we subtract off all of this stuff. So this is 0 to the 5th. Okay. Minus 5/4 times 0 to the 4th plus 0. I don't know why I put 2 there. 0 squared, which in this case, these are all zeros, so it's kind of nice. It's nice when you have a 0 and everything is going to just get thrown out. So we're just going to be left with whatever that is. And in this case, it turns out to be a minus 48 all over 5. Okay. All right. Next problem. The integral from 0 to 1 of 5x squared times 4x cubed minus 2 to the 4th dx. Okay, this is where we need u substitution. Here is something that I need you to pay very close attention to this, okay? In this problem, when we do u substitution, we also have to substitute the bounds. So right now, this thing right here and this thing right here, those are both in terms of x, not u. So here's what I'm going to do. I notice when I do my u substitution, the derivative of this is going to equal something like that, so that works out well. Okay, that's what we wanted. So we're going to let u equal 4x cubed minus 2, and when I do the derivative, du is equal to 12x squared dx. All right. And then I can just divide through by 1/12. 1/12 du is equal to x squared dx. Okay. Good. Now, here's the thing. This is an x, that's an x, but I want them to be u's. So all I have to do now is I take that value of 0, my lower bound, and I'm going to plug it into my u is equal to 4x cubed minus 2 as an x value, okay? So if x equals 0, that means u is equal to 4 times 0 cubed minus 2, which is equal to a minus 2. So this is going to be like my new lower bound, okay? Suppose x equals 2. That means that u is going to equal 4 times 2 cubed. Oh, sorry, it's 1. What am I doing? X equals 1. Sorry about that. 1 minus 2. So 4 times 1 is 4, minus 2 is going to be a positive 2. Okay? And the order does matter. So if I'm going to 0, 0 and minus 2 have to match up. 1 and 2 have to match up. So in other words, this thing right here turns into minus 2 to 2 of, 5 times 1 over 12 u to the 4th du. So 5/12, which is going to be just 5 over 12 times, and then the integral is we increase it by 1 to the 5th and then divide by 5. So 1/5 u to the 5th plus c, but we're not going to do the plus c obviously, so then it's going to be between minus 2 and 2. Okay? So that cancels with that, and I'm going to be left with 1/12 u to the fifth between minus 2 and 2, which means that this is equal to 1/12 times the upper bound first. So we do 2 to the fifth minus 1/12 minus 2 to the fifth. So 2 to the fifth, 2, 4, 8, 16, 32. 32/12. That's what this is. And then over here, since it's to the fifth, it's minus 32 minus a minus is a plus. So this is going to be plus 32/12, which is equal to 64/12. And this is equal to 16/3. Okay, so that's our final answer. In fact, if you want, let me actually show you this because I think it is a really handy kind of tool. Give me just a second here. I got to get it organized. So let's go to Wolfram Alpha, and I'm going to do both of these. So the integration, again, it's just really helpful to know how to do this integration because there's some that is it's just a total pain to try to do it unless you, to do it by hand, it's a little bit easier, honestly. So here we've got our sum, or our integration, and our lower bounds. I'm going to do the original, so 0 to 1 of 5x to the 2 times 4x to the 3 minus 2, to the 3 minus 2 to the fourth. And this is dx. And if I hit enter, you'll get a solution of 16/3. Okay, so that's actually what we got. But let me do the other one really quick. So if I change this around to minus 2 to 2, and this is going to become, let me delete all this stuff. What do we have? It was 5/12 u to the fourth. So 5/12 u to the fourth. And then this is going to become du. Okay. Oh, of course it's going to give me a problem. Just do it with x. It's fine. Just pretend it's an x. There we go, 16/3. Okay. So there it is. It's the same thing. It works out perfect. All right. Let's go back to our notes. So I'm going to go ahead and continue on, do the next problem. So you always need to make sure that if you're using u substitution, you also substitute the bounds as well. Okay. So this next one, from 0 to 4, the square root of 4x plus 9 dx, okay, which is the same thing as 0 to 4, 4x plus 9 to the 1/2, okay, dx. So I'm going to let u equal 4x plus 9. du is equal to 4 dx, which means that 1/4 du is equal to dx. And now I got to do my bounds. So when x is equal to 0, u equals 4 times 0 plus 9, which is equal to 9. And then when x is equal to 4, u is equal to 4 times 4 plus 9, which is equal to 16 plus 9, which is 25. Okay, so my integral becomes 9 to 25 of, let's see, u to the 1/2 du, and it looks like we've got the 1/4 there as well, so that has to come along right there. It can be, again, you can put it in the inside or outside, it really makes no difference. So sometimes, like in the previous question, you saw me put it inside. In this instance, I put it outside. It makes no difference whatsoever. It's just a constant. If you've got variables that are kind of escaping, that's a problem. You need to make sure the variables always live after the integration sign, but when you have just the constants, either one is perfectly fine. Okay, so this right here is then ultimately going to become 1/4 times 1/2 raised to the 1 power by 1 is going to be to the 3/2. And then I'm going to multiply by the reciprocal of whatever that is. So that's going to be times 2/3. U to the 3/2. Okay? And this is going to be between 9 and 25. So as a result, this stuff is all going to cancel out. So I get 1/2 times 1/3, which is equal to 1/6. U to the 3/2. And again, one of the nice things about doing it in this way with switching everything to U's is you don't have to worry about going back and back substituting anything. Like you just keep it there and live with it. It's partially why I prefer this method, but you know, tomato, tomato, it's the same thing. 25 to the 3/2 minus 1/6 times 9 to the 3/2. And this is actually going to work its way out to being 49/3. Okay. All right. Let's do another one. Ooh, I like this one. Next one. Suppose I've got integral from 0 to 2 of x over x squared plus 4 dx. Okay. So I'm going to let u equal the thing with the higher exponent, so x squared plus 4. That means du is equal to 2x dx, which means 1/2 du is equal to x dx. All right, so then this thing, first off, let's actually take care of the u's as well. I forgot to do that. So if x equals 0, that means u is equal to 0 squared plus 4, which is equal to 4. And x is equal to 2. U is going to equal 2 squared plus 4, which is equal to 8. Okay? So these are my new bounds. So I'm going to go from 4 to 8 of, what is it, 1/2. I'm going to stick this on the outside just so you can see really quick. 1/2 times this, and we're going to have du over u. But notice this right here is a logarithm, okay? When you see du over u, you immediately think logarithm, okay? So this is 1/2 natural log absolute u, evaluated between 4 and 8, which in this case is just going to be 1/2 natural log of 8. Absolute value of 8 is just 8, so I'm just going to put it as that, minus 1/2 natural log of 4. And we can actually use some of the properties of logarithms to work this one out. So this is actually going to be the same thing as the, so the 1/2 can go to the, as an exponent on the 8, natural log of 8 to the 1/2, minus natural log of 4 to the 1/2, which is equal to the natural log of the square root of 8, minus natural log square root of 4, which is equal to, in this case, natural log of square root of 8 is the same as 2 root 2. So you can, again, I'm kind of going a little like ham with this one. You don't have to go this far, but just for the sake of practice, I think it's just good. This is going to be minus natural log of 2. And using the properties of logarithms here, because we're subtracting, that is the same thing as the natural log of 2 root 2 over 2, which is the same thing as the natural log of just root 2. Boom, there it is. So if you punch this into Wolfram Alpha, you should get the exact same thing up above. Kind of nice. All right, let's go ahead and move on to the next one. Let's do the integral from 0 to 2 of x squared plus 1 dx. And they're asking, in this question, I mean, they literally, it's just contextual. It's pretty much the exact same thing, but they specifically say, what is it? Where is it? Find the area between the graph of x and the x-axis. Basically, that's the integral. Okay, so you just have to find the integral of this thing, which is the same thing as the integral from 0 to 2. We don't need u substitution here because, I mean, you don't need it. It's just, you can do each of these individually. So x squared is going to be the same as, oh, here, I don't know why I'm writing this out. Let's do this. So this is going to be 1/3 x cubed plus 1 is going to turn into an x, and now I'm doing the evaluation between 0 and 2, and then I can sub these in. So 1/3 times 2 cubed, that's a 2, plus 2 minus 1/3 0 cubed plus 0, which is equal to 2 to the third, 2, 4, 8 over 3. So 8/3 plus 2, that's all 0. And so this should be the same thing as 6/3 plus 8/3, which is 14/3. Right? So that's our solution. Okay. And again, you know, I mentioned this earlier, but you can use Wolfram Alpha to help and double check your solutions. There is a way to do this in the graphing calculator. I don't even know if anyone's using a graphing calculator in this course, but there's a ton of different ways to use that actually, and to determine the area between two different x values on the curve. So if you graph it, you can actually determine what it is on the graph. But I'm going to leave that as an exercise to you for how you want to do it. And that comment, by the way, is mostly from my online class. If you're taking my class face-to-face and you're just watching this as like a reference, I'll show you how to use that in class. All right, let's do this one more problem. So this is a healthcare cost question. The total annual healthcare costs in the United States, actual and projected in billions of dollars for selected years, are given on the table in the equation. Or the equation, I guess they give us the equation. So they give us a table, but the equation they give is y is equal to 4.447 x squared minus 9.108 x plus 1055.4. Okay. This models the annual healthcare costs of y, which is in billions of dollars per year, as a function of the number of years. So x is a number of years. Okay. Use a definite integral and this model to find the total cost of healthcare over the period from 2005 to 2015. So it's important to note that this is the number, x is the number of years past 1990. So this 2005 would correspond with x equals 15, and 2015 would correspond with x is equal to 25, okay? That is insanely important, because if you try, if you sub these in as your bounds, oh my gosh, your number is going to be outrageously large. So let's just go ahead and sub these in. So we're going to do the integral from 15 to 25 of 4.447x squared minus 9.108x plus 1055.4. This is all dx. Okay. So this is what we need to do. We need to determine what that is. You can actually do this by hand. It's really not terrible. If you had to do like U substitution or you had really more crazier values, you certainly would have, kind of your own fair share of problems. But this is going to be 4.447. We're increasing the exponent by 1, so you're just dividing that by 3. So this is going to be cubed minus 9.108 divided by 2 x squared plus 1055.4 x, and then we're evaluating between 15 and 25. Okay. So you can go ahead and sub, each of these values in. You sub the first one in. Now, actually, I'm going to write this out because I think it is important. 4.447 all over 3. The reason why I'm writing this out is because the common problem that a lot of people make in this specific type of problem is as follows. Hang on. I need to talk slower because I haven't gotten there yet. 25. Okay, now this is the kind of problem that people face. They'll do this. Minus 4.447 over 3 times 15 cubed minus, this is the problem. They'll only subtract off that first one. You need to make sure you subtract off everything that's inside, okay? 9.108 all over 2 times 15 squared plus 1055.4 times 15. Close it off. And then this, you can actually determine what it is going to be 26,891. Which, by the way, this is equivalent to, this is in billions of dollars. So if I've got thousands of billions, that would be trillions. So this is 26,891,000,000,000 over the span of that 10-year period from 2005 to 2015. That's how much is estimated to have been spent on healthcare, which is, I don't know if you know how big $1 trillion is, but it's a lot. That's a big amount. So if you want for fun, not that, if you want to, I would encourage you, go ahead and take a look. There's some kind of simulation videos that will actually show you the difference between like 1, 100, 1,000, 1 million, 1 billion, 1 trillion. It's absolutely insane. So go ahead and take a look at it. It's pretty crazy. Okay, that's all I have for today. We're going to go through some more content here the next time. Hopefully this integration, and you're getting really comfortable with the integration. Hopefully you're getting comfortable with doing some, with this definite integral stuff. Just really kind of taking that indefinite integral, and then we're just kind of adding an extra step to it. So if you do have any questions, feel free to let me know. But I hope you have an absolutely fantastic day.